Hello students, today we'll be discussing the solutions for chemistry CET test 2 and we'll be discussing solutions which are based on the chapter alcohols being inside. Okay, let's start our discussion. The first question, which of the following combinations can be used to synthesize ethanol? Ethanol. So what kind of alcohol is ethanol? So we know that ethanol is a primary alcohol, right? CH3, CH2, OH. So ethanol is a primary alcohol. The functional group OH is attached to a carbon which is in turn attached to only one carbon. So ethanol is a primary alcohol. And we know that just observe the options over here. So it's all Grignard reactions, right? All the reactions are Grignard reactions. So we know that when formaldehyde reacts with Grignard reagent, we will be getting primary alcohol. When other than formaldehyde, other aldehyde reacts with Grignard reagent, we will be getting secondary alcohol. And when ketone reacts with Grignard reagent, we'll be getting tertiary alcohol, right? So now in this option, this is ketone obviously, and this is an ester. You cannot get ethanol from this. And this is alcohol and Grignard reagent. Obviously, we cannot get the alcohol from this. Alcohol from alcohol again we cannot get. So coming to this, right? Straight away, it's formaldehyde and CH3Hg. How can we get ethanol from this? We look into the mechanism. It's just this formaldehyde, HCO. I'm adding Grignard reagent, CH3 Mgi. Okay. Between carbon and magnesium is electropositive. So, and carbon is electronegative, isn't it? So now this carbonyl bond is polar carbonyl. This bond shifts and you'll be having negative charge over oxygen, positive charge over carbon. Your carbon in carbonyl will always act as an electrophile, right? It's electrophilic in nature. So now this CH3 minus will attack this carbon. This, right? So now we'll be getting, I'll write this CH as CH2 O minus, and to this magnesium iodide is attached, Mg. Okay? And to this carbon, this CH3 is being attached, isn't it? CH. So now, this upon hydrolysis will get CH3, CH2, OH. Right? We can take H plus and OH from this hydrolysis, and this H plus will attack this electronegative oxygen, and OH minus will attack. We will get this byproduct as well. Right? Now I got ethanol from formaldehyde and methyl magnesium iodide. So this has to be your answer. Okay. Next question. The correct order of boiling point for primary, secondary, and tertiary. Very easy and straightforward question. So we know that boiling point is directly proportional to number of carbon atoms. Okay. But here, obviously, if we have primary, secondary, and tertiary alcohols, number of carbon atom is same. But what can we observe? We can observe branching, isn't it? And your boiling point is inversely proportional to branching, right? For example, if I take some propanol or butanol, let me take simple butanol, which is primary, right? This is primary. Now I will take secondary. Now this is secondary. Now I'm taking tertiary butanol, right? So now what is happening when I'm moving from primary to tertiary? The branching is increasing, right? You have branch one branch over, have three branch over, right? The branching is increasing. As the branching increases, your surface area decreases. Right? Surface area is decreasing. As the surface area decreases, obviously the van der Waals force of attraction also decreases. As van der Waals force of attraction decreases between the molecules, we're breaking those force of attraction because there are less number of van der Waals force of attraction, right? So that's why your boiling point also decreases. So the boiling point order should be this. The primary alcohol should have higher boiling point than secondary, which will be having higher boiling point than tertiary, right? Because as the branching is increasing, your surface area is also, sorry, branching is increasing, your surface area is also decreasing. As the surface area decreases, your van der Waals force of attraction decreases and boiling point also decreases. Okay? So I think the correct option is A. Coming to next question, catalytic dehydrogenation of primary alcohol gives, very easy question. Catalytic dehydrogenation means dehydrogenation. That means we are removing hydrogen, H2, and we have to remove hydrogen from primary alcohol. So let me take this RCH2OH. This is the primary alcohol, right? Now, if I remove one hydrogen from here and one hydrogen from here, obviously I'll be removing two hydrogen. Okay, you will be getting that R, C, double bond O and H. So you'll be getting RD, right? Where this is a simple reduction, right? It will yield RDI. Next. Okay. Next question. An organic compound A containing CHO has a pleasant odor with boiling point of 78 degrees Celsius. On boiling A with concentrated H2SO4, a colorless gas is produced, which decolorizes bromine water and alkaline KMN, right? The organic liquid areas. We have to find out what is. This is a very straightforward and simple question, and they have given several hints in this question. If you just observe this pleasant odor, your alcohols will have a pleasant odor, and we have only one alcohol over here. And the second hint is on boiling A with concentrated H2SO. So what happens when you add concentrated H2SO4, any acid to alcohol? Dehydration takes place, isn't it? Dehydration. So alcohol upon dehydration will yield alkene. So I just write this CH3, CH2, OH. We add H plus, water will move out, and one hydrogen carbon will move out, and you'll be getting CH2 double bond CH2. The alkene dehydration to give, right? Now we know that alkenes react with bromine to give Vicinal dibromide, right? CH2, Br, CH2, Br. This particular reaction we have studied in preparation of haloalkanes, and we have also studied this particular reaction in hydrocarbon chapter, right? So the bromine is a brown color liquid. So earlier, when you just add bromine to the solution, it will be brown in color. So when bromine reacts with alkane to form vicinal dibromide, the brown color gets changed to colorless. The thing is, it is decolorization. Decolorization of bromine is happening, and that happens only when you add bromine to alkane, right? So alkane, how did you get alkane? Alkane will be produced only by adding acid to the alcohol, right? So obviously alcohol should be. And they've also given this hint that alkaline KMNO4 also degrades. Yes, and that happens only with this, right? So the option is C, C2H5OH. The compound, fifth question, the compound which gives turbidity immediately with Lucas reagent, yes, at room temperature, right? So this is a very easy question. We have discussed that Lucas reagent is anhydrous zinc chloride and HCl, isn't it? The mixture. And when we add Lucas reagent to tertiary alcohol, we'll be getting an alkyl halide. And as soon as alkyl halide forms, the turbidity appears, right? Since tertiary alcohol are highly reactive, they will give or they will show turbidity immediately than the other alcohol. So if you add Lucas reagent to secondary alcohol, obviously even it will show turbidity by forming a secondary alkyl halide. But after some time, not immediately, right? And with primary alcohol, we know that the reaction happens very slow when you add Lucas reagent. So at room temperature, it won't show turbidity. After some time, it will show turbidity. So it has to be a tertiary alcohol. Now in this option, we have to choose a tertiary alcohol. Butane 1-ol, obviously this is primary alcohol. Butane 2-ol, this is a secondary alcohol. Now observe 2-methyl propane 2-ol. What is this? 2-methyl propane 2-ol. It's a tertiary alcohol, right? 1, 3, 4, H. This is your tertiary butyl alcohol, right? So I'm going to take this as my parent chain. 1, 2, 3. This is 2-methyl propane 2-ol. This is a tertiary alcohol. Now this tertiary alcohol will react with Lucas reagent and will produce a tertiary alkyl halide so that it gives turbidity immediately. This has to be your option number C. Okay. Question number 6. Which of the following will not react with sodium hydroxide? This thing we have discussed in the concept of acidity of alcohols and bases. Right? So your phenol will react with sodium hydroxide and it will form sodium phenoxide very quickly because it is more acidic than alcohol. But when you treat alcohol with sodium hydroxide, alcohol is not acidic enough to react with sodium. So this will not react with sodium hydroxide very easily. It has to be your alcohol, C2H5OH. Okay. Next, coming to question number 7, denatured alcohol is. Okay, this is a factual based question. The denatured alcohol is ethanol plus methanol, right? Ethanol is a drinking alcohol. So now we add methanol so that the commercially the ethanol which is being used for commercial purpose should not be used for drinking. For that reason, we'll be adding methanol to ethanol, and now the alcohol is said to be demethyl. Coming to question number 8, the conversion of metanitrophenol to resorcinol involves respectively. This is a good question. Look, we have a metanitrophenol, right? So nitro group at meta position, right? So I have to convert this metanitrophenol to resorcinol. So what is resorcinol? So this is your resource. Okay. Now what should I do? I mean, the changes should happen at this position, right? So nitro group should undergo some change. So in all the option, you can observe three things. One is hydrolysis, reduction, and dilution. So I will start with a reduction. Okay. Reduction means addition of hydrogen or removal of oxygen. So if I remove O2 and add H, and add H2. Okay. So nitro group on reduction will give NH2. Okay. So after this, I will conduct diazotization. Diazotization means your NH2 group will turn into N2Cl, right? Diazonium chloride. So this is N2 plus Cl minus, the diazonium chloride reaction, right? I converted into diazonium. Next, this upon hydrolysis, okay, what can happen? I can take H plus and OH minus. We know that our nitrogen gas is very good leaving. Okay, this will leave, and H plus and Cl minus will form HCl, and remaining is your OH minus will attach. OH will attach to this group, right? So you will be having this OH and OH, right? So now I got resorcinol from this. And the course of reaction should be this. First, it should be reduction. We'll be converting nitro to NH2. And then after, when I conduct diazotization, carry out, when I carry out diazotization, I'll be getting into diazonium chloride. And when this is hydrolyzed, you'll be getting this. So the option should be this, D, reduction, diazotization, and hydrolysis. Coming to ninth question. This question is a mixture of two reactions. The first reaction is CHCl3 and KOH, very famous reaction, trimer-dimer reaction. And after this, we'll be observing Canizar reaction. So this trimer-dimer reaction belongs to alcohols, and this belongs to aldehyde bonds. Right? So now what happens when you treat phenol with potassium hydroxide and CS? You'll be getting salicylic, right? H, EHCl3, QOH. So I got salicylic. Now, this is X. Okay. Now we have to find the final product. Now I'm adding 50% KO. So whenever you have an aldehyde which does not have alpha hydrogen atom. So now what is alpha hydrogen atom? This is my functional group, and the carbon next to this carbon is an alpha carbon, and the hydrogen attached to this carbon should be an alpha hydrogen. Since I don't have any other hydrogen, this has to be, since I don't have alpha hydrogen, this can undergo Cannizzaro reaction. The condition for Cannizzaro reaction is that you should not have an alpha hydrogen. So now I don't have alpha hydrogen in this particular molecule or my salicylic. So this can undergo Cannizzaro reaction. When I'm adding KOH, what are the products of Cannizzaro reaction? When you add KOH, you'll be getting alcohol CH2OH and potassium salt of carboxylic. Right? So option B should be your answer. Question number 10. Correct acidic order of the following compounds. Okay. So one thing we know that when we add electron withdrawing group to phenol, acidity increases, right? And when we add electron donating group to phenol, acidity decreases, right? So because it will stabilize the phenoxide ion. Whenever you have an electron withdrawing group like NO2, the phenoxide ion which forms after removal of H will be greatly stabilized. That's why your nitrophenols, 4 nitrophenols or 2 nitrophenols, nothing but ortho and para nitrophenols are highly acidic in nature. So third should be first in the order. Next, coming to this is your paracresol, right? You have CH3 at para position, and you have an electron donating group over here. So CH3 is an electron donating group. We know that electron donating group will decrease the acidity. So obviously this should have least acidity. Next we have metachlorophenol, right? Chlorine is an electron withdrawing by inductive effect, right? And it is at meta position, it will obviously withdraw electrons. So it can act as an electron withdrawing group, but it cannot be as strongly as electron withdrawing as nitro, and that too nitro is at para position. At para position, it can act as a strong electron withdrawal. So chlorine position should be second. Okay, this has to be order. So where is this? Sorry. This is second, right? CH3. Chlorine is first. So third, first, and second. This is first. First is your nitrophenol, and next is your chlorophenol. Next is your cresol. So third, first, and second. Okay. Next, coming to 11th question. Phenol is treated with some reagent. It forms a tribromo derivative X. This is an easy question, right? We know that phenols are highly activated. when I add bromine water to this, I can get tribromo derivative because it is highly activated at ortho para position, ortho and para position. All these positions are highly susceptible to electrophilic attack. Okay, whenever you add bromine water, obviously you will be getting tribromo derivative. Okay, so it should be. On reacting with neutral ferric chloride, phenol gives 12th question. This can serve as a test for detection of phenol. Whenever you add ferric chloride to phenol, okay, it will form a violet colored complex. Okay. It will form a violet colored complex. So from this we can know that whatever that I have taken is a phenol. Okay. Should be option C. Coming to question number 13. CH3, CH2, OCH. What is it? It's an ether. Ether reacts with hot and excess hydrogen iodide, then formed product X. They have mentioned excess. Okay, so this is a reaction of ether. What happens when I add hydrogen iodide to ether? CH3, CH2, okay. First thing is protonation, right? This lone pair electrons on oxygen will attack this H plus and it will get protonated. Plus I. Now, in the second step, what happens? This I minus will attack either of this. Because both are symmetric in nature, they are symmetric. It's a symmetrical ether. Right? So these oxygen has got positive charge. Obviously, it wants to take electrons. It will take these electrons. And now this carbon has become electron deficient. The nucleophile will. So this is a nucleophilic substitution reaction, and that to your SN2 reaction specifically, because your nucleophile is attacking from the opposite side that of the leaving group, right? So I will be getting CH3, CH2, OH plus CH3, CH2 I, ethyl iodide. Now, we cannot stop here because they have mentioned that they have taken excess of hydrogen iodide. Now, the alcohol formed can again react. It can again react with hydrogen iodide. So what happens if it again reacts with hydrogen iodide? This oxygen lone pair will attack this H plus and it will form CH3, CH2, O, H, H. Right? Now this H2O H2O is a good leaving group. It will leave and you have I minus in your solution, right? H plus and I minus. This iodide will again act as a nucleophile and it will attack this carbon and we will be getting CH3, CH2, I, right, as your product. Now, I got 2 moles of CH3, CH2, iodide, ethyl iodide, here as well and here also, right? So, answer should be this. I'll get only this because I've taken this in excess. I've taken hydrogen iodide in excess. Okay. Moving on to question number 14. In which case methyl tertiary butyl ether is formed? Methyl tertiary butyl. First, it's better to write down the structure, right? CH3 O C H, right? So this is methyl tertiary butyl. So we know that if I take an alkyl halide which is tertiary in nature, and if I try to react this with sodium alkoxide, I'll not be getting this methyl tertiary butyl because obviously we can observe this. We have this tertiary butyl group, we have this methyl group, but this reaction does not happen and it won't give this particular product. It will actually give you an alkyl, right? Because this alkyl halide is highly sterically hindered. Now, your sodium methoxide can act both as a nucleophile and a base. So when you have a bulkier alkyl halide, it prefers to act as a base rather than act as a nucleophile. It prefers to take away hydrogen and mode of this particular group and act as a base rather than acting as a nucleophile and attaching to this group. Okay, so now this from this reaction I cannot get this, right? I cannot get this. So the only reaction, the only way to get this particular ether is by taking opposite of this. I'll take tertiary butoxide, sodium tertiary butoxide, and I'll take an alkyl halide, simple methyl bromide, or sorry, simple methyl chloride, anything is fine. Okay, now this will act as a nucleophile and it can attack this smaller methyl. This I can get CH3 CO6, right? So I can get methyl tertiary butyl ether from this particular reaction. So do we have this option? CCH3ONA. This I can write this as CH3 thrice ONA and plus CH3 C. Okay. So now look out for this option. I think this option is correct, right? CCH3 thrice. This should be your answer. B. Okay. Moving on to next question. In the reaction, they have given this particular reaction. This is where reacting anisole, right? This particular molecule is anisole with HBr. What can happen? This is a reaction of ether. The reaction of ether, right? This can attack this HBr and you can get particular intermediate. Now, I will be attacking BR methods. This is same as the previous one, right? You want to get an alcohol and alkyl bromide from an ether, right? So where will this nucleophile attack? The thing is, I can break either this bond or this bond, right? But if I break this bond, I'll be getting phenyl carbonate. So this is highly unstable, right? Even the SN1, we know that SN1 and SN2, both kind of reaction does not happen with your aryl substituted groups, right? So that's why I cannot break this bond. I will actually break this bond. How? This oxygen will take these two electrons and you will be getting OH. And since the oxygen is taking with these two electrons, this carbon becomes electron deficient and this bromide will attack this carbon and it will form CH3Br. Right? So you'll get this product. So it's option B then. Propane 1-all can be prepared from propane. Okay, this question should be propane. Okay. This is a straight question, and we know that if we want propane 1-all, it appears that the product is being formed via anti-Markovnikov's addition, right? So this is your propene. And if you are getting propane 1-all, CH3, CH2, CH2OH, so the negative part has been added to carbon containing most number of hydrogen atoms. So obviously this product is obtained via anti-Markovnikov's addition. And we know that whenever we have B2H6 diborane, the hydroboration oxidation reaction, you will be getting anti-Markovnikov product, right? So all these will be eliminated. You will be having obviously your acid. Whenever you add acid, you'll be having Markovnikov's addition. This is mercury acetate and water is again your oxymercuration and demercuration reaction. Again, it will yield Markovnikov product, isn't it? So obviously, this option C will yield you anti-Markovnikov. That's your answer. Coming to question number 70. Dehydration of the following in increasing order is. Okay. They have asked you dehydration. That means it will be removing OH in the form of water. So obviously, we can add H plus to this, H plus, and then this will move out as water. So dehydration reaction rate would be high when the carbocation which is forming would be stabilized, right? So in the dehydration step, dehydration reactions, you'll be having a step wherein you'll be getting a carbocation. So obviously the reaction depends upon the stability of this carbocation, right? So now we have to observe which carbocation formed by dehydration would be stable. If the carbocation is stable, then the dehydration reaction occurs very quickly, right? So now let's observe this. If I remove this OH and water, I'll be getting this carbocation, right? So now what happens? This carbocation can be stabilized adjacent pi bond by conjugation, right? Have one pi bond, it is in conjugation with the other pi bond, you have two pi bond, more conjugation, right? Observe. Observe option 3. Here, if I remove this OH as water, I'll be getting this particular carbocation. Obviously, this carbocation is also stable, but here you have only one conjugation, not more than multiple, right? So what's with second option? Second option, if I get this particular carbocation, this is secondary carbocation. All these are secondary, right? Even this is your secondary, even this is. But this is more stable by the electron delocalization for here, right? But this is a simple secondary carbocation which could be stabilized by the inductive, right? Over here. What about this? If this undergoes dehydration, you will get a phenyl carbocation, which is highly unstable. So obviously, this should, this first compound, phenol, does not want to undergo dehydration. So it should be at less position. It should be at last position, right? So look out for the option where first compound is at last position. So this, this is eliminated. Now I told it fourth you will be having highest stabilization, right? So obviously this should come at first. We have this over here. This. Next should be 3. Fourth, then 3, then your 2, then right? It has to be this. 4, 3. Option A. Oh. Question number 18. The correct order of the solubility of different alcohols in water. Okay. Alcohols are soluble in water. We know that because it can form hydrogen bond. It can form hydrogen bond. Right? This can form hydrogen bonding with water, right? Now, this R part, your alkyl or aryl part in your alcohol, is hydrophobic. That means it does not like water. So when I increase the size of this R part, your alkyl or aryl part, when I increase the size, your solubility will decrease, right? Solubility will decrease. So now observe. You have ethanol, propanol, and butyl alcohol. So what happens? In ethanol, you have two carbon or two CH2. You'll be having CH3, CH2. Here you'll be having three carbon. That means more hydrophobic. Here you have butyl means you'll be having four carbon, right? Which has more hydrophobic group than propanol. So when you move from ethanol to butyl alcohol, the solubility should decrease, right? Ethanol will be more soluble than propanol, which will be more soluble than butyl alcohol, right? Because your alkyl group size is big, that's why your solubility decreases. Option A. Okay. Okay. Coming to question number 19. Sodium phenoxide reacts with carbon dioxide at 400 Kelvin and 4.7 pressure to give, yes. So this particular reaction is coal-based reaction, isn't it? We'll be taking phenol and when you add sodium hydroxide to this, you'll get sodium phenoxide. H plus will be replaced by sodium phenoxide. Now, this on treatment with carbon dioxide, what will you get? You will get CHO, right? Now, this particular compound, what I have got right now, is sodium salicylate. Sodium salicylate. Now, if I add acid in next step, I could get phenol. I mean, this ONA will be replaced by OH, right? Na will be replaced by H. So you'll be getting OH group. So this would be your salicylic, right? Now, since they have not mentioned this the addition of H acid at the last step, the answer should be this sodium salicylate. They have just asked you what happens when sodium phenoxide reacts with carbon dioxide. I've reacted carbon dioxide with sodium phenoxide. I'll be getting this sodium salicylate. Only this, right? right? So the answer should be your sodium salicylate. They're just asking this. Coming to last question regarding this topic. The number of isomeric alcohols of formula C4H10O. Okay, C4H10 is, I can write CH3, CH2, CH, CH2OH, right? We have 1, 2, 3, 4. 4 carbon atom and 1 oxygen atom, and 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogen. So this is your butane, no, right? Butane. So now we have to find out the isomers, right? So one would be this. Next, what can I do? I can take CH3, CH, CH3, CH2, OH. Can I take this? Okay, 1, 2, 3, 4. I have 4 carbon atoms, and 6, 7, 8, 9, 10 hydrogen atoms, and 1 oxygen. So this could be the other one. CH3, C, CH3, CH3, OH. 1, 2, 3, 4 carbon atoms. 3 is a 9 plus 1, 10 plus 1 oxygen. This can also be your another isomer, right? Okay. So what could be the fourth isomer? I'll take this C, OH. I've just changed the position of your OH. CH2, CH3, 1, 2, 3, 4. 4 carbon atoms, 3, 3, 6, 7, 8, 9, 10. 10 hydrogen and 1. This can also be your another isomer. So totally I can have 4 isomers. And obviously I don't think so that we can have any, right? We cannot make any other isomer of this. So it should be your 4. Okay. I hope you all understood the solution for these questions regarding the chapter alcohols and phenols. Thank you. Thank you, students. Happy learning.